Okay, allow me to share my screen. So you can now see on the slide, Roman numeral 2. This is actually the second option in terms of determining the value of the n and the k from the set of empirical data that is given. So we have covered the first one, that's the empirical rate equation of nth order. Or if simply stated, it is just a more generic manner of writing the rate law for whatever the value of n and k is. And as a review, this is our empirical rate equation for nth order reaction. Okay, now for this afternoon, we will continue with determining the n and k still. That way, we are able to give the n and the k for a particular reaction given a set of data for to be interpreted. Now, in here, you're not given the, I should say, the concentration and the time pair of data, but rather in this case, you are given the half-life, and paired with the half-life is the initial concentration of that particular reactant in a particular system. So your pair here of data will be initial concentration and the half-life. From that initial concentration and the half-life, you are to get the order of the reaction. You are to come up with the order of the reaction and the rate constant. Now, we have a pre-derived formula already that is suggested by Levenspiel in his book, Chemical Reaction Engineering, the third edition. In this equation, on the left side, you have the half-life. And this 0.5 here is the degree of conversion since it's half-life. So of course, our understanding would be that 50% of the reactant was converted at this particular half-life or the time that is indicated. So we're going to raise that to 1 minus n, and this term should be subtracted by 1. Now, the denominator is k times the quantity n minus 1, and this rational expression should be multiplied to CaO raised to 1 minus n. Now, as it is written in our textbook, this k that you see in here with the block on top is like the average k, or the k and y. This k and y actually is taken from the rate constant of the reaction multiplied to these particular expressions raised to a certain exponent based on the stoichiometric equation provided. Now, to simplify things, we will not anymore have to worry about converting this k and y to k, but rather whatever is the k that we get out of this particular formula that is written here, that would be the k that should be reflected in the rate law. So if I may say, if this is our rate law, generally represented in this manner, the k and y that is written in the formula is this k that is written here. So there's no need for you to determine the k here given the stoichiometric equation from the k and y that was taken from the formula. Whatever is the k and y here, it's the k that is written in here. Primarily because class, this k and y and this k here are, shall I say, more or less the same. If they should vary, if their values should vary from one another, there is only negligible variation. So we just go for the k and y as the k in here that should be written in the rate law. As for the n, that's the same n that you have in here. Now, in problems such as this, you will be given the empirical set of data, as I have mentioned already, will come in the pair of the half-life together with the initial concentration. So it's like I use this particular initial concentration, what would be the half-life? Then I ran a separate test at a different initial concentration and measure the half-life. So in this case, in order to determine the order and the rate constant for a particular reaction, you run a series of steps at different initial concentrations of A, of your species that you'd like to use as a basis in determining the rate of your reaction, and correspondingly measure the half-life for such initial concentration. So how will you determine the half-life? You simply have to measure the time when this initial concentration is already half of its original value. Then that is already the half-life that is to be paired here with this particular initial concentration. So as to determine again the N and the K, using the half-life method, there should be a series of runs that should be conducted at different initial concentrations. And the corresponding half-lives to these initial concentration values measured. Now, how is it done? So it's in here. It's still probably, shall I say, more or less anchored upon linearization of the differential equation using the techniques that you have learned in your DE. So what's going to happen is this. It's explained in here. The half-life method requires a series of runs at different initial concentrations. So after which the ln or the log of the half-life is plotted versus the log of the CAO or the ln of the CAO. The slope of the best fit line is equal to 1 minus n. So knowing the slope, you equate it to 1 minus n. That would be then giving you the n value. After you have already determined the n value, using the initial concentration and the half-life, that's the T, you can go back to the rate law that you have written and determine the rate constant. So what do I mean by that? So let me annotate. So let's say, for example, you have here dCA, dt, and you have written it in a manner that is generic. Upon using this particular procedure, you plot the log of the half-life, the ln of the half-life to the ln of the CAO. So your original data, so I should have 4 rows here. Your original data that should have T and that should have CAO. You need to compute the log of the, by the way, this is half-life. So the log of the half-life and the log of the CAO. So from the two original pair of data, you are to come up with this, and then you're going to do the plotting. Now, you may say, this Miss Ali is already graphical, right? So, do graphical na siya. But it could still be converted to purely analytical way of determining the N and the K. Now, if I may ask you, how would you do it? Because in here, you're going to look at the instruction or the suggestion that is given in the text. You are to plot. So the term that is used is you are to plot the log of the half-life versus the log of the CAO. Now, if we are not going to plot, how will you come up with the N? As it's stated here, which is equated. So you have the 1 minus n, which is equated to the slope of the best fit line. How will you come up with it? If I may ask you, if you're not going to do plotting, because we will not do plotting, you're going to solve it later on when you have a problem. You can do the plotting if you're in front of your computer and do the Excel, use the Excel, then you can get the slope of the best fit line. In your case, if you don't have your computers in front of you and you only have your calculators, how will you go about finding the N? Okay, there is this suggestion in the inbox. Make an equation of the line. Okay, so Drexel, thank you. You make an equation of the line. Okay, so this is our equation. I like to clear first my markings. This is our equation, Drexel. How am I going to come up with the equation of the line? From that equation, how am I going to come up with the equation of the line? Since you are to come up with an equation, you say you come up with an equation of a line. How am I going to come up with that equation? Actually, even if you don't need to come up with the equation of the line, as already suggested, you already have a ready-made suggestion in here. You can already find the slope of your, the slope, and then you can find that after the slope, you can find the order of the reaction. Now, if this is our working equation, how do I find the equation of the line as you have suggested, Excel? Anybody here who can tell the class on how can we get the equation of the line from the formula? Okay, we'll just open Jamboard, that way we can write there. Anybody? Jack said you have suggested that we write the equation of the line. Now our working equation is this. How do we come up with that equation of the line that you have suggested? Come on, think. How will you come up with the equation of the line? Which, first and foremost, after that you have the equation, you will actually be, again, it will just be simply a validation of the suggestion of what's going to be done. How would you do it? Or what's the equation of the line? No suggestion? No idea? That said, you must have an idea because you said you're going to come up with an equation of a line. So how is that going to be? What would that procedure be? Okay, I will share the Jamboard and I will show to you how you come up with the equation that Drexel is suggesting. Actually, that's correct. That way you will have a clearer understanding of the procedure that was suggested in our textbook. That way you can come up with the order of the reaction. So the working formula that we have is this. So original working formula is the half-life equal to, we have the K times the quantity n minus 1. Here in the numerator you have 0.5 and you have 8 raised to 1 minus n. You have your minus 1. This is multiplied to CAO raised to 1 minus n. So I am writing it in here. From this formula that is already pre-derived, you are going to come up with the equation of the line. I'm going to ask you, how am I going to get a linear equation from this particular formula? What should I do? I should get the ln of both sides of my equation, or I should get the log of both sides of my equation. So it would be something like this. Okay. And then what will happen? You have here, I place a dot in here, so meaning you are multiplying these two expressions. As a property of your log in differential calculus, it's just like adding two ln's with these arguments in here. So the first ln that I should have is ln of, so I'll have 0.5 raised to 1 minus n minus 1 k n minus 1. The other ln will have this, the ln of CAO raised to 1 minus n. These are the two expressions here that are being multiplied, and as a property of ln, it can be split into two ln's, taking the sum of the two that is. So if I will now rewrite this properly, I have ln of the half-life equal to, I will just rearrange. We have also this property of the ln wherein this 1 minus n here can be written before the ln. So you have 1 minus n ln of CAO plus we have this entire expression ln of, we have 0.5 raised to 1 minus n and minus 1. And here you have k raised to 1 minus n. I like to use a different color font since you will see. So you will see. As suggested, you are to plot the log or the ln of the half-life, that should be the y, versus this one, the ln of the CAO. This is your x. And from that plot, you will get the slope of that line. This is the m. And this entire expression here, after you have taken the n, if you have the y-intercept, you can get the k, or the k and y, which is right away now our k. So you can see that this is an equation of a line. It's a linearized form of the original equation for determining the half-life given the value of the initial concentration. Of course, it has to be known. I'm referring to the rate constant, and the order of the reaction should be known. So this is it. So that's the reason why it says there that you are to make a series of runs at different initial concentrations. You take the ln of that, and that should be your x, and you plot it against the ln of the half-life at that particular initial concentration. The line will have a slope. The best fit line, that is, will have a slope, and you equate that to the expression 1 minus n here, because that's the slope of your line now. Now, after you have determined the n, you go back to this particular formula here for the y-intercept. Substitute the n that you got from here, and you can solve already for the k. Now, the suggestion of Drexler, I went to presenting it here to you. That way you can understand why. If I go back to our slide, the suggestion was, just share it. The suggestion was this. So now you will understand why you have to plot the ln of the half-life versus the ln of the initial concentration. Or it could be log. It doesn't matter whether you use the log or the ln. Anyhow, they have the same properties. Now, I'll go back to my question a while ago, a few minutes ago. I said, let's say, for example, you're taking a board exam. You're taking an exam wherein you don't have your laptop, you don't have a computer wherein you can do this plotting that is suggested in here. But it's still possible, as I have mentioned, that you can determine, using this particular suggestion here, the n and the k. So my question is, how will you do that? Using your calculator, what will you do to get the slope of the line that will give you the order of the reaction, and then get the y-intercept of that line that will also give you the rate constant of the reaction after you already determined the n. So what will you do with your data now? So that was my question. How will you make, or what's your alternative plan? That way, from a graphical approach here, you can analytically determine the n and the k. What would you do? I'll go back to the Jamboard. What would you do? Let's say this is your raw data. What would you do? No idea. Then how are you going to solve a problem if it's given to you? You will be needing a laptop beside you. Is this the first time that you have encountered or heard of such a question? How will you determine the slope of a line and the y-intercept of the line given pairs of data without you having to resort to graphical approach? What would you do? Okay, it seems like you have zero idea. I don't know why a third-year student, a fourth-year chemical engineering student would not have any idea at all what to do about this. Slope is equal to delta y over delta x. That's correct, Excel. What I'm trying to ask is this. Maybe you don't get the question. You cannot, let's say you don't have a laptop, you don't have a computer beside you, you're given a pair of data, this one, the half-life and the initial concentration. Now the problem of course will require you for the n and the k. So as suggested, you get the ln of these two and you are to plot. So this one is your y and this one is your x, okay, as presented to you in the equation a while ago. So you want to plot these two. That way you can get the slope of the best fit line using this information. So meaning this raw information that you have here, you take the ln, you will have a new set of data. This raw information that you have here, you take the ln of that, you will have a new set of data. Now, as suggested, you plot. I'm saying you cannot plot unless otherwise you only want to solve a problem for 1 hour because you have to do the plotting there. You have to find a graphing paper, whatever you have there, and plot and get the slope of the best fit line. I don't think that's engineering at all. So now I'm asking you, based on the tool that you have there, your calculator, that's the only one that you have there, how are you going to find the slope of the best fit line? That will help you determine the n. How will you find the y-intercept of the best fit line? That will help you find the k after you already determine the n. So this is already the n time that I asked. What will you do? What will you use, or how will you use your calculators? That way you get to find the slope of the best fit line. What will you do? The slope is 1 minus n, and the b is the ln of 0.5 raised to 1 minus n minus 1 over k times, let me check if I have written it properly, n minus 1. So it seems like you need this and you need this for you to get this and this. That's what. So how will you find this one? Using your calculators. Are you done with statistics already? Are you finished with your statistics already?
Yes, miss.
Okay, you're finished with your statistics. Did you discuss linear regression?
Yes, miss.
Oh, see, how did you go about using your calculators, processing information using your calculators, linear regression? You use the stat mode of your calculator using linear regression, you'll be able to get the slope of the line and the y-intercept. Now, that's beyond the scope of this subject already because it's already a tool that I have assumed that you know already. So I will not cover it anymore. So what you're going to do, you review on that linear regression using your calculator. I think you have to place it on statistics mode. And your calculator, based on the inputted data that you place there, will give you the slope of the line and its y-intercept. From that slope of the line value, you can solve for the n. From that y-intercept value, together with the n that you have solved here, you will be able to get the k. So please review that linear regression. So that's the answer that I have been looking 30 minutes na ko gapamangkot regarding linear regression. So you have to review on how you're going to use your calculators, linear regression application. That way you can find the slope and the y-intercept of the best fit line. Because in here you'll be using that. You will not going to graph anymore because graphing will not help you find the answer in a faster manner. Okay? So I leave that to you to check on and review. I will not discuss it here anymore. So I'll go back to our slides. And that's it. if you're given a set of data that is half-life and initial concentration, this is how you're going to find the order of the reaction from the slope of the best fit line. Okay? Now, another method is the fractional-life method. It's really comparable to the half-life method that is shown here. The half-life method has this 0.5 in here as the fraction of the species A that has been converted during the half-life period. So that is why it's 0.5. 0.5 of it was already converted. That's half-life. In fractional life method class, let me just clear this one. In fractional life method, this could be any fraction. So the formula is exactly the same as this one. Only that we did not specify f to be 0.5. So this f could be 0.3, this could be 0.2, this could be 0.7. So this particular half-life method measures the time it would take for a particular initial concentration of reactant A to reach, let's say, 70% conversion. So in here, you're going to place 70% if it's 70% conversion that is stated in the problem. If it's not 70%, let's say if it's just 30% or 25%, this should be also following that particular information that is stated in the problem. So actually, if you already have this formula, this general formula for the fractional life method, the half-life is just a special equation coming from this because it's just the same. You just simply specified here that the fraction converted is 50%. So if a problem does not give you 50% conversion, let's say 70% conversion for different initial concentrations, and you're given the corresponding time it would take your reactant to reach that particular conversion, then you still have to use the same, exactly the same procedure that is stated here for the half-life method. Exactly the same, because in this case, class, in the fractional life method, what you will be given would also be the time it would take for that fraction to be converted and initial concentration. So this would also be your row data. So just like the half-life method, you will have to add 2 rows here, taking the log or the ln of this fractional life and this initial concentration. Still, the best fit line will have the slope of 1 minus n. And of course, the order of the reaction could be determined from that. It's the same thing with the intercept of your best fit line. The same equation as the half-life method. So if you can read here on the note, the plot of the log of the fractional life versus the log of the CaO gives the reaction order just like the half-life method. So both of these particular techniques are given in Levin's field just in case the problem does not give you specifically the half-lives at different initial concentrations. But rather, the problem might give you the fractional life at different initial concentrations. So the formula is exactly the same. You just change the F for whatever fraction of conversion is specified in the problem. You get it? So it's the same formula, it's the same approach as you do with the half-life method. Now, I will just move on. These are very important generalizations regarding the use of the fractional life method in determining the order and the rate constant for a particular reaction. Now, number 1, if your n is greater than 1, the fractional conversion increases with increased concentration. So for orders of reaction greater than 1, as we increase the initial concentration, the fractional conversion also increases. What is this fractional conversion that is being referred to in here? This is referring to the F. So the greater the initial concentration, the greater is the conversion if the order of the reaction is greater than 1. What about if it's less than 1? So fractional conversion decreases with increased concentration. So we increase the concentration of our reactant, the fractional conversion decreases. When is this? When n is less than 1. This includes n values which are negative. Now, what about if the order of the reaction is really equal to 1 in the case of the fractional life method? Fractional conversion in this case is independent of initial concentration. So for orders of reaction which is equal to 1, actually it's just only 1, it's just 1, your fractional conversion is not dependent on the initial concentration. Whether it's high, whether it's low, the fractional conversion is independent of it. When is that? When the order of the reaction is equal to 1. So take note of that. This is for the fractional life method, of course, including the half-life method, because a fraction will also include the half-life there. Now, let's go to multiple reactions. So far in the, if I may say, in the 40% of this slide on interpretation of batch reactor data, we have only covered single reactions. Okay, what about multiple reactions? So we will go into each of the reactions now. So the first of these multiple reactions that we're going to cover is the irreversible reactions that are said to be competing or parallel. So I have written it in this manner here, but majority of the textbook would write it in this form. You have a single reactant, and from that particular single reactant, you have two reactions happening simultaneously in the formation of two products. So this is a parallel reaction, and it's written, if it's written in this manner, it would be easily explained later why you come up with these particular expressions for the rate. Okay, but in books and in reference materials, this is how it is written. Now, note both reactions are assumed as elementary. So you are to assume that these simultaneous or competing reactions are elementary in nature, even if it's not mentioned in the problem. Now, when you write the net rate equation based on the species that is being converted, in this case, that's A. So the rate of A is equal to the negative of the change in the concentration of A with respect to time. And you have to write down the rate law for each of these assumed elementary reactions. So you see, it's K sub 1 C sub A plus K sub 2 C sub A. Now, since C sub A is common between the two terms here on the right, you can factor out that C sub A, and that gives you this equation, which has now two rate constants which are added, which you can easily actually add because they are constants. So looking at the DE that you have here, this is easily evaluated using separation of variables. Okay, because you need only to add the two rate constants there. Now, that's one way of expressing the rate of this parallel reaction in terms of A. Now, if we write the rate of reaction in terms of the products R and S, so we have two products. So, since these are products, we write the rate of change of the concentration of R and S with respect to time as positive. And this time, you write the rate constants here as K sub R C sub A and K sub S C sub A. I wrote it as K sub R and K sub S because you're now expressing the rate in terms of different species R and S. In here, you have expressed the rate in terms of A. So this K sub 1 and this K sub 2 is expressed in terms of A, or rate constants in terms of A. If we have to use another rate constant in a rate law based on a different species, that rate constant should also be correspondingly labeled based on that species. So you can write it as K sub R for R and K sub S for S. Now these are your three rate expressions based on the reactant A and based on the products R. actually you can write here K sub 1A and K sub 2A. Specifically meaning these two rate constants were based on species A, but the first one is for the first of this competing reaction, and the second one is of course for the second of these competing reactions. Now, if you're going to process these three rate equations, you will have this formula. So I will just clear my markings here. If this one is processed, okay, the first one based on species A, this will be the corresponding expression after separation of variables. I think this is very self-explanatory. If you're going to get, sorry class, if you're going to get the ratio of these two, you get to cancel the dt's and the dt's here. The CA and the CA here is going to be canceled. You will be left with this expression. Okay, the rate of R divided by the rate of S is equal to dCR dt, dCS dt. The dt's will cancel. This is K sub R C sub A and K sub S C sub A. So the C sub A is also cancelled. So this is the remaining expression. Now, where is this coming from? You may wonder, where is this coming from? So this dCR, sorry, class. Just because something came up here. Can't see. What's wrong with this? Let me just stop sharing class.